So I was looking at this week's worksheet, and I noticed that Dr. Moraine really only had you look at cases with these chair conformations where you had both both substituents either both of them were either axial or both of them were equatorial, but you didn't really have very many where one was axial and one was equatorial. So I wanted to do one of those, trying to see. Yeah, pretty much all of them are both axial, both equal. I wanted to do one of those, so I basically took one of the ones from the worksheet and modified them. I'm going to draw the structure of trans 1-tert-butyl 3-methyl-cyclohexane in the chair conformation, which I suck at drawing, so this should be comical. Oh wow, I wasn't kidding. It really was awful. Anyway, we're gonna work with that. We're gonna make it work. All right, so it's a trans 1,3-cyclohexane. So that means that one is axial. One of these substituents, either the tert-butyl or the methyl, will be axial, and the other will be equatorial. So I'm just going to call this carbon 1, because why not? And that's going to have our tert-butyl on it. So I'm going to draw this one in axial. And then I guess I'll go ahead and label it A to help, whoever looks at this after me understand whether it's axial or equatorial. And then I'm going to draw this hydrogen down over here to the side to make it look equatorial and put an E by it. Now I recommend definitely drawing in your hydrogens. You should absolutely draw in your hydrogens for every for every carbon connected to a non-hydrogen substituent. So here's carbon 1, and I'll make this carbon 2, and this will be our carbon 3, which has the methyl on it, right? And it is trans. So if this one's up and axial, and for this to be 1,3 trans, then this one has to be down and equatorial. So here's your methyl, down equatorial. And then it's going to have an up and axial hydrogen. So I'm just going to point it straight up and draw an A by it, just to be clear. So now it wants you to do the second possible chair conformation, i.e. the ring flip. So I think we all did really well with these, so I'm not going to really go through how to do it. Let's see what even happens with this next chair. I think this is the way you're supposed to draw, like with a 2. And then something happens here, and then it looks okay. Yeah. I don't think I ever did these in Organic 1. I know I didn't understand the ring flip at all when I took Organic 1. So I pretty much learned it like 3 weeks ago. But luckily it's not that complex. Anyway, so the ring flip, as we know, just basically cycles everything through clockwise 1 carbon. It's not actually, these substituents are not, keep in mind that these substituents are not actually detaching from this carbon and moving to this carbon. That's not what's happening. It's just that this thing is kind of like folding itself up in a way that this carbon kind of ends up moving from here to here, and then this carbon ends up moving from here to here. So you get that sort of like clockwise rotation. But it's not a chemical transformation at all. There are no bonds breaking or forming. It's just kind of like, I don't know if you studied like proteins or something in biochem. It's kind of like folding around in like weird ways. So then after the flip, here's your carbon 1, right? And here's carbon 3 after everything happens. Before this was up and axial, right? So now it's going to be up and equatorial, the tert-butyl. So I'm just going to kind of draw it like this. It's not clear. It clearly is not clear that this is up and equatorial. So I'm going to go ahead and draw this hydrogen down like this to make it clear. That's why I recommend drawing the hydrogens. And then this one was down and equatorial before, so now it's going to be down and axial after. And then I'm going to draw this hydrogen in kind of up and off to the side, but not completely straight up, so you can tell that it's not axial. And so now it wants you to label any 1, 3 diaxial interactions. So let's go ahead and start with this one. It's going to have this 1, 3 diaxial interaction here between this hydrogen. And there should also be a hydrogen here to contribute with. So every substituent should have 2 1, 3 diaxial interactions. And then there's a 1, 3 here too. I'm not really sure how I wanted to draw that. And so these occur between the tert-butyl in this one, since it's in the axial position in this one. So in this one, the only axial interactions can happen between the methyls and the hydrogens. So there's one here. I'm going to draw in a 1, 3 here. And then this hydrogen also contributes. That's all the 1, 3 diaxial interactions in this molecule. So now I want you to determine which one is the most stable, and this is where this is the one case where it gets a little tricky, and this is why I wanted to make this video. All right, so basically in this case you have 2 competing substituents. You have your tert-butyl, super bulky, and then you have your methyl, which is super light. The super bulky, just like with the Newman projections, the overlap of something super bulky with anything else is always going to be greater in energy than the overlap of something super that's super light with something else. So here where you have all the diaxial interactions between the tert-butyl and hydrogens, this is going to be your least stable. And remember, with the methyl, with the whatever's in the equatorial, you don't really need to consider it because it's just too far away from everything else to really interact with it electrostatically. And then in this one, you have the methyl group that's interacting with all the hydrogens, and so it's lighter than or it has a lower molecular weight, and basically at the atomic level, like lower molecular weight basically translates to less charges that are interacting with each other and destabilizing electrostatic interactions. So this is your most stable conformer, because you have your smaller substituent in an axial position and your larger one in the equatorial position, where it's kind of flanked off to the side and it can't interact with anything else in the molecule. And this is the way most of these molecules probably would be in solution or something, if you thought about it that way. But anyway, good luck. Hopefully she doesn't give you one of those on the exam. Hopefully they're pretty straightforward.